Hello students, good morning and welcome to another video lecture of physics. Now in this video lecture basically we are going to discuss about permanent magnet and electromagnets, right? As well as at the end of this video lecture we are going to solve few MCQs which are very important, right? Quite important for your entrance exam as well as for your board exam. So let us start discussing about permanent magnets. What are permanent magnets? Permanent magnets are basically those material which can retain ferromagnetic property for longer period of time. अगर हमारे पास कोई material है, right, and that material can retain ferromagnetic property for long period of time, then such materials are known as permanent magnets, right? So this is the definition for permanent magnet. अगर हमारे पास कोई material है और वो material ferromagnetic properties long time तक retain कर सकता है, then that material will be known as permanent magnet. So permanent magnets are those material which can retain their ferromagnetic property for longer period of time are known as permanent magnets. Clear? Now how to prepare permanent magnets? Basically permanent magnets, how we can prepare? So look, in some book which were published before 400-500 years, in that a method to magnetize a material was shown. It means that to produce permanent magnet is quite old method, right? We were knowing how to prepare permanent magnets from, let us say, 400-500 years. So how to make a permanent magnets? Remember, you can prepare a permanent magnets in 3 or 4 different ways. The first method is आपको एक rod लेना है, right? And this rod you have to place in north south direction. ये rod को north south direction में place कर दो, right? Now keep on hammering this rod. Then you will find that this rod will be converted into permanent magnets. But ये rod ferromagnetic material का होना चाहिए और it should be a steel material, right? और alnico, that we are going to discuss. अगर हमारे पास एक special type of rod है, right? Then if you keep on hammering that rod, then this rod will be converted into permanent magnet. और ये rod को आपको अर्थ के north south direction में रखना है. The reason behind this is if you keep on hammering this rod, तो इनके जो इलेक्ट्रॉन्स होंगे they will gain some energy, and due to the external field of earth these electrons will change their orientation, right, their orbital motion in the direction of external field, so that we will get net magnetic dipole moment, and hence this rod will be converted into a permanent magnet. This is very old method to prepare a magnet, right? This we were using before 400-500 years to prepare a magnet. Now जो दूसरी method है, in that what we have to do is basically अगर हम एक steel rod ले ले, then we have to rub this steel rod with a magnet. Suppose ये magnet का north pole है, let us say this is the north pole of a magnet, right? तो हमें इसको इस तरह से rub नहीं करना है. You have to keep on rubbing this rod with the same pole. पोल चेंज भी नहीं करना है. सपोज यू आर टेकिंग नॉर्थ पोल, तो नॉर्थ पोल ही लेना है एंड कीप इट ऑन रबिंग इट वन डायरेक्शन. मीन्स इफ यू आर रबिंग फ्रॉम डाउन टू टॉप, तो यहाँ से डाउन टू टॉप, रिमूव इट, अगेन डाउन टू टॉप, अगेन रिमूव इट, डाउन टू टॉप. एक ही डायरेक्शन में इसको आप रब करते जाओ, राइट? इन दैट केस दिस स्टील रॉड विल ऑल्सो बी कन्वर्टेड इनटू परमानेंट मैग्नेट्स. But the best way to get a permanent magnet is take a ferromagnetic material and place it inside a solenoid. एक ferromagnetic material लेके उसको solenoid के अंदर रख दो and allow current to pass through that solenoid. Right? In that case, the material will get magnetized and it will retain its magnetic property for longer period of time, depending on the type of material. Remember here, in order to prepare a permanent magnet, we should select such a material which has 3 qualities. First one is it should have high permeability. The second one is it should have high retentivity, right? And the third one is it should have high coercivity. So the material should have high permeability, it should have high retentivity and high coercivity. Now what is retentivity and coercivity, right? So if you draw a graph of B versus H, which we have already discussed, let us say here we have magnetic field B and here we have H, right? H is IF and all that. Now if you plot a graph of this B versus H for a ferromagnetic material, then the graph will be something like this. Here we'll get saturation magnetization, again saturation magnetization back to point A. This is O, A, let us say B, point C, D, E, F and A. This will be the direction. Right. So this curve is known as hysteresis, which we have already discussed. Now this point B and C, this point B and C correspond to retentivity and coercivity. Here point B is known as retentivity. Why retentivity? Even if you make current zero, the material will have some magnetic property. It will retain some magnetic property. That's why we are calling this as retentivity. And point C represents coercivity, means the amount of current required to demagnetize the material. Right. So अगर हम कोई मटेरियल सिलेक्ट कर रहे हैं in order to make it permanent magnet, then हमें ये तीन चीजें माइंड में रखनी है. These three things you have to keep in mind, that the material should have high permeability, high retentivity and high coercivity, so that the material will remain magnetized for longer period of time. अगर ये three qualities material में है, then the material will remain will retain its magnetic property for longer period of time, or it will remain permanent magnet, right? So here the material which we select for preparing permanent magnet must have these three qualities, and actually you can say that steel is the material which is best for making permanent magnets compared to soft iron. Remember, soft iron do have high retentivity, but it has very less coercivity compared to steel. Steel do have less retentivity compared to soft iron, but coercivity of steel is very large, right? And hence instead of soft iron we should use a steel rod to prepare a permanent magnet, right? Because it has high coercivity, high retentivity and high permeability. Now यहाँ पे जो high retentivity है, it will make sure कि material has strong magnetic field, it is strongly magnetized. High retentivity will make sure that material is strongly magnetized. On the other hand, high coercivity will make sure that the material is not erased, the magnetic property of the material is not erased by some external magnetic field, fluctuation in temperature, or you can say that a minor damage, right? This all thing will not affect the magnetic property of that material if there is high retentivity and high coercivity, and that's why we are using steel to prepare permanent magnet. The other materials which can be used to prepare permanent magnet is alnico, right? One is of course steel and the other one is alnico. Aluminum, nickel, cobalt and copper. Combination of these four things will give you an alloy, and that alloy is used to make permanent magnet. Clear? Now we do have electromagnets. So what are electromagnets? Basically electromagnets are temporary magnets. Means if you allow current to flow through them for some period of time, then that period of time only it will behave like a magnet. अगर हमारे पास कोई magnets है, electromagnets, right? And if and only if you allow current to pass through it, then only it will behave like a magnet. Otherwise, they will lose their magnetic property. As soon as current will become zero, they will get demagnetized. Clear? And that's why they are known as temporary magnets or electromagnets. So how to prepare this kind of temporary magnets or electromagnets? Basically, the best way is to take a soft iron rod and place that soft iron rod in a solenoid. Let us say this is the solenoid. In this solenoid, we will place a soft iron rod. Right. So this is the soft iron rod inside this solenoid. Right. Now allow the current to pass through this solenoid. As a result, the material will get magnetized and it will have some magnetic property. As soon as current will become zero, it will get demagnetized, right? So you can say that a soft ferromagnetic material is used as a electromagnets or temporary magnets. When current passes through it, during that period of time only it will behave like a magnet. As soon as current will become zero, it will get demagnetized. Basically, this kind of electromagnets are used in electric bell, right, loudspeaker, right. In this kind of instrument we are using electromagnets. For electromagnets, retentivity is very large but coercivity is very less. Retentivity is large but coercivity is very less. So you can say that to prepare a permanent magnet, we should have a hysteresis curve, broader one, right? In case of temporary magnet, we should have a curve which is narrow curve. The material which has this kind of figure, like if we get a hysteresis curve like this, then this material is best suitable for temporary magnets, and if we have a broader one, then it is best for making permanent magnets. Now in case of soft ferromagnetic material, generally what happens that most of the energy will be lost due to eddy current, right? Like in the coil of transformer. So what is eddy current, what is transformer? You will come across this topic in chapter 6 and 7. But in those cases, energy will be lost due to production of heat. Eddy current will be produced and that current will produce Joule's heat, I square R, right? I square RT. So heat energy will be produced and its energy will be lost. Means whatever amount of current we are supplying here, that will not be used completely to magnetize the material. Some energy will be lost in case of electromagnets, right? And this loss is due to the magnetization and demagnetization of the soft ferromagnetic material, which is constantly kept in an AC supply voltage, right? In some application, the material goes through an AC cycle of magnetization for longer period of time. Look, electromagnets should be used for smaller period of time, right? But there are certain applications in which the material will go through AC cycle for longer period of time, of magnetization for longer period of time. Now in that case, what will happen? Basically, there will be loss of energy, right? Such applications are like, you can say that for transformer. In case of transformer, right, the material will be magnetized and demagnetized continuously for a longer period of time. So in such cases, eddy current will be produced, right? And this eddy current will decrease the output energy. There will be some loss of energy. The energy which you are supplying and the energy which you are getting as the output will always be less than the input energy. So there is some loss of energy due to magnetization and demagnetization of material. As well as eddy current is produced, then according to Joule's heat, there will be energy loss, right? So for such material, the hysteresis curve should be narrow, as we have discussed, so that we can minimize the energy loss. Remember, we cannot reduce the effect of eddy current. You will come across this eddy current as well as transformer in chapter 6 and 7. At that time, we will discuss about these things. But for time being, if hysteresis curve is narrow, then the loss in energy will be very less. But for broader curve, there will be large amount of energy loss, right? So here, this figure is suitable for producing electromagnets. For electromagnets, hysteresis curve should be as narrow as possible, right? The area of this curve will represent the loss in energy due to magnetization and demagnetization of material due to eddy current, right? So these are electromagnets. Now basically electromagnets, as I have said, are used in electric bell as well as a loudspeaker, but we do have some giant electromagnets which are used in cranes to lift heavy loads. Clear? Now we are going to solve 2-3 MCQs which are quite important for your entrance exam as well as board exam, right? So the first one is, suppose we have a steel rod. Suppose we have a steel rod of length L. Let us say the length of this rod is L and its magnetic dipole moment is M. we have a steel rod of length L and its magnetic dipole moment is M. Now if this rod is bent in the form of a circle, semicircle, sorry, suppose we are bending this steel rod in the form of semicircle, then what will be the new magnetic dipole moment? If you bend this steel rod in the form of semicircle, then what will be the new magnetic dipole moment? Look, what is magnetic dipole moment? We know that magnetic dipole moment is defined as pole strength into length. Of course, you are writing 2L into P because there we have considered length as 2L. Here length L is given. So basically magnetic dipole moment is pole strength into the length of that material, right? So P into L. Here length is L, right? Length we should consider between two end points. So here these are the two end points, right? So what will be this length? Can we say that this length will be nothing but diameter? So you can say that here length L dash will be equal to 2R, right? Diameter. How to find this L dash? Here rod is same only. So you can say that here length of the rod will be equal to half of the circumference because it is semicircle. So 2 will get cancelled out. So length will be equal to pi r. So you can say that r will be equal to L by pi. So therefore 2r will be equal to 2L by pi. This will be the length of this semicircle, right? Length means the distance between two end points we have to consider. Now new magnetic dipole moment will be M dash will be equal to pole strength is same only because end we are not cutting or something like that. So pole strength is same into length is 2r and 2r is 2L by pi. So you can write this as 2 by pi into P into L. P into L is M. So you can say that this is 2M by pi. This will be the new magnetic dipole moment when the steel rod is bent in the form of semicircle. Now the same question can be asked that you are bending this rod from the center in such a way that the angle between them is 60 degree. Let us say 60 degree. So in second case we have the same steel rod of length L only and we are bend its magnetic moment is M. Suppose we are bending it from its midpoint. Let us say if this has north pole and this is south pole, and if you bend from the midpoint such that the angle is 60 degree, means like this we are bending this steel rod. Angle is 60 degree, right? Right. So basically you are cutting it into half of its length, right? And we have discussed in our last video lecture that if you cut a bar magnet into half of its length, its magnetic moment M dash will be equal to M by 2, and here also let us write M1 and M2. M1 and here M2 will be equal to M by 2 because length is half. Look, if M is equal to P into L, now if you bend this, we'll consider this as two different magnets of length L by 2, L by 2, right? So M dash will be equal to P into L by 2. That is equal to P into L whole over 2. Now P into L is initial magnetic moment, so it will be M by 2. So here magnetic moment of this will be M by 2 and this rod, let us say this is 1 and this is 2. So magnetic moment of first one will be M by 2 and second is also M by 2. And this angle is 60 degree. Look, if this is north, this is south, and if you consider this as two different things, then this will be north and south. Magnetic dipole moment is always from south to north. So here in this case, magnetic dipole moment will be in this direction, right? South to north. For first one, let us say M1. And for second case, it will be in this direction. South to north, right? This is M2. This angle is given as 60 degree. So if you want to use law of parallelogram, the angle which we have to consider is this, that is 120 degree, right? And according to law of parallelogram, this is first one and this is second one. This will be the resultant magnetic moment. This has magnetic moment M1, this has magnetic moment M2, and this will be MR, which is the resultant magnetic moment. So the formula for resultant magnetic moment using law of parallelogram will be equal to MR is equal to under root of M1 square plus M2 square plus 2 m1 m2 into cos theta. Here 120 is there, so cos 120. Remember here 60 is given, but actual angle will be 120 between these two magnetic moments, vector quantity, right? Magnetic moment is a vector quantity. So between these two magnetic moments, angle will be 120 degree. So m of r will be equal to m by 2 whole square plus m by 2 whole square plus 2, let me write here only, 2 into m by 2 into m by 2, and cos 120 is minus half. 2 into m by 2 into m by 2 into minus half. So you can see that this 2 will get cancelled out. So this will be equal to root of m by 2 whole square plus m by 2 whole square plus m by 2, and this plus into minus will be minus m by 2 whole square. So this term will get cancelled out, square and square root will get cancelled out, so your answer will be m by 2. Look here, angle was 60 degree, that's why we are getting m by 2. If angle is 30 degree, right, then this will be 150 and your answer will be different. Clear? Pause this video and copy this to MCQ. These are the two most important MCQ for you. Okay. Now let us discuss few more MCQ. Like the first one is, suppose we have a bar magnet and its pole strength is P. Now if we cut this bar magnet in such a way that the ratio of their length L1 is to L2 is 2:1, then what will be the ratio of their pole strength? Remember here, when a bar magnet is cut perpendicular to its length, then its pole strength will always remain same. If you cut a bar magnet perpendicular to its length, then its pole strength will always remain same. So your ratio of pole strength P1 is to P2 will always be 1:1. It is always same. The second one is magnetic field lines. So magnetic field lines and options are given. So the best option is magnetic field lines always form a closed loop. You have to remember this, magnetic field lines always form a closed loop. Electric field lines will never form a closed loop. On the other hand, magnetic field lines always form a closed loop. Right. Next is, pole strength of a bar magnet is 5 ampere meter and its length is 5 centimeter. Let us say 10 centimeter. So that is 0.1 meter. What is its magnetic dipole moment? So magnetic dipole moment is P into L. So here P is 5 and L is 0.1. So that is 0.5 ampere meter square. So magnetic dipole moment will be 0.5 ampere meter square. Next MCQ. The force acting on a magnetic pole of pole strength P is given as 7 into 10 to the power minus 2 ampere meter, and force is given as 31.5 Newton. Then what is the magnetic field? Right. So we have formula like, remember F is equal to Q into E. Right. So in the same way for magnetic field, F will be equal to, instead of Q we will write P, pole strength. Instead of electric field it will be magnetic field B. So this implies that B will be equal to F by P. So here F is 31.5 divided by 7 into 10 to the power minus 2. So 31 divided by 7. So 7 4s are 28.5 into 10 to the power minus plus 2. So answer will be 4.5 into 10 to the power plus 2 Tesla. Clear? So these are the few MCQs for this video lecture. In next video lecture we are going to discuss few more MCQs like this from chapter 5. But before that, I have already provided you an assignment, right? So just go through that, solve that assignment, and if you find difficulty while solving some MCQs, please let me know so that we will discuss that in our next video lecture. Thank you.